This is a solution to problem 11.5 from your textbook. This is a very interesting problem because, as we're going to see over the next few pages, this is going to combine a lot of the circuit analysis techniques that we have learned from previous chapters and ultimately allow us to get into some average power analysis. So what we're given here is this schematic. We've got a voltage source, which is given as 8 cosine 2t minus 40 degrees volts. So we know from this that omega is 2. We have a 1 ohm and a 2 ohm resistor arranged as so, a 3 Henry inductor, and a 1/4 farad capacitor. And we're tasked with finding the average power delivered to each of the passive elements. So the first thing I would do if I were tasked with solving this is to convert my schematic into the frequency domain. So you can see here I've got a phasor to notate my 8 cosine 2t minus 40 degrees, just a magnitude of 8, and an angle phi of negative 40 degrees. I'm leaving my resistors as they are, and I'm converting my inductor and capacitor into impedances. As you see over here, the inductor is just j omega L. So omega being 2, L being 3. That works out to J6 ohms for the impedance of the inductor. Likewise, the impedance of the capacitor is 1 over J omega C, omega being 2, C being 0.25. This works out to be 1 over 1/2 J. And if you don't want to keep the J in the denominator there, this ends up just being negative J2 ohms. And so now we have this in complex representation for all of the impedances that we have in the circuit. So the first thing that I would want to do to figure out the power is I'm going to start with this 1 ohm resistor here on the left and see if I can figure out the voltage across it and the current through it. So in order to do that, I'm going to do some impedance combination. I'm going to go ahead and combine this 2 ohm and the negative J2 ohm into one impedance and just call that a 2 minus J2 ohm impedance. This is a serial combination. Then what I'm going to do is find a parallel combination of the J6 ohms representing the inductor and the 2 minus J2 ohms representing the series combination of the capacitor and the 2 ohm resistor. And what I'm going to ultimately find is that that equivalence is given by just a 1 over Z1 plus 1 over Z2. And so then I'm going to end up finding a common denominator here. Ultimately I get to this, multiply the top and the bottom by the complex conjugate of this complex pair right here. And so at the end of the day, my equivalent for those two works out to be 72 minus J24 over 20. So that is my equivalence for these two in parallel. Now what I'm going to do is treat this as a voltage divider, where this is my voltage, 8 phasor, negative 40 degrees, a 1 ohm resistor, and this equivalent impedance that we just calculated as 72 minus J24 over 20. We're going to treat that as a voltage divider, and so down here I want to know how much voltage is across the 1 ohm resistor. So I take my voltage of my input, multiply it by the impedance of the 1 ohm resistor, just 1 ohm, divided by the total impedance, which is going to be 1 ohm plus that ZEQ that I just calculated. And so I'm going to go ahead and multiply by 1 and realize that's not going to do anything to my numerator. Down here at the bottom, I'm going to convert this 1 into just 20 over 20, so I add that to this, and that goes from 72 to 92. And so then what I'm going to do is go ahead and divide both of these quantities, because 4 divides in evenly. I'm going to divide them by 4, make this 23 minus J6, and then the remaining 5 I'm just going to multiply up here. So this is going to go from 8 to 40. So that's how I'm distributing this 20. And so this works out to be a phasor. I'm going to convert this complex in the denominator back to phasor. So my R is just going to be 23 squared plus 6 squared, and my angle phi is going to be the inverse tangent of negative 6 over 23. And so that, as a phasor in the denominator, works out to be 23.77 phasor negative 14.62 degrees. And just to divide these two phasors, remember I divide the two R values. That's what you see here. So 40 over 23.77 gives us 1.683. And we subtract the two angles. So negative 40 minus a negative 14.62 works out to a negative 25.38 degrees. And so that is our voltage. Now we want to figure out what is the current through that. Well, it's just going to equal the voltage divided by this 1 ohm resistance. And so that's actually going to work out to be the same phasor, except now it's going to be in amps. And so we go back to our formula for the average power, and we realize that the average power of a component can be given as 1/2 the real portion of the phasor for the voltage multiplied by the conjugate transpose of the current. And all we need to do in phasor notation to get that conjugate transpose is just flip the sign, S-I-G-N, sign of the angle for the current. So when we're multiplying this through, it's 1/2 the real portion of, here is our voltage phasor, here is our conjugate transpose of current. It looks exactly like the current phasor, except now we flip the sign from a negative 25.38 degrees to just 25.38 degrees. As you multiply these together, you realize this ends up being 1.683 squared, and then as you add the two angles, they add to 0. And so if you're trying to find 1/2 of the real portion of this, what you notice is when you have 0 degrees, that means the entire thing is real, because the cosine of 0 is going to be 1. You're not going to have any imaginary because the sine of 0 is 0. So if you were to break this phasor back into components, your real component would be 1.683 squared cosine of 0, and then your imaginary would be plus j times 1.683 quantity squared sine of 0. The sine of 0 is going to 0, and so the entire thing is real. So all you need to do is say, okay, what is 1/2 times 1.683 squared? If you do out 1.683 squared, you get 2.832. Dividing that by 2, the power delivered to the 1 ohm resistor is just 1.416 watts. Now, let's do a very similar approach for the 3 Henry inductor. And what I'm going to observe is that the voltage across the 3 Henry inductor is just going to equal the voltage of the source minus the voltage that's dropped across the 1 ohm resistor. Let's review why that is. Let's go back to our schematic. So if this is Vs at this node, and I want to figure out what is the voltage across this inductor, I can just take Vs and subtract off however much voltage gets dropped across the 1 ohm resistor. I just calculated the voltage that was dropped across the 1 ohm resistor. I already have it as a phasor. That was calculated right here. And so I'm going to use that value and I'm going to subtract it from the phasor that I had over here. So what that's going to tell me is that this is going to be, this is my Vs phasor minus my V of 1 ohm phasor. Now in order to subtract two phasors, I have to convert them back into the complex pairs that they represent. And so this is going to equal 8 cosine negative 40 degrees. That's the real portion coming from this phasor, plus j times 8 sine of negative 40 degrees. That's the imaginary portion. And then likewise we do the same thing over here. R cosine phi minus j times r sine of phi right in here. Okay, and so we have that, and then when we combine those components, this ends up being 4.608 minus j times 4.42. Convert that back into phasor by taking the square root of the sums of the squares of the horizontal and vertical components, or the real and the imaginary components. Get the angle by taking the inverse tangent, making sure to leave it in degrees, of the imaginary portion divided by the real portion. And so that works out to be 6.385 phasor negative 43.807. And so here we want to figure out the current going through there. So we're going to take that voltage and we're going to divide it by the impedance of the 3 Henry inductor. Remember, the impedance of the 3 Henry inductor is J6 ohms because omega here is 2. So J omega L is our impedance there. Omega was 2, L was 3, so we get J6 ohms. So now I'm going to go ahead and convert this J6 into a phasor. And I can do that basically by inspection. If you think about it being on a real and imaginary axis, this is a positive value, but it's all imaginary, so that means it's all along the imaginary axis, which is going to be a phase offset of 90 degrees. And so you've got an R value of 6. That's what you have here, and you're going to have 90 degrees. So if you divide these through, you get 6.385 divided by 6. That is this 1.0642. And then you get phasor. You subtract these two, you get negative 133.807 degrees. So now we do a similar approach. The average power delivered to the 3 Henry inductor is 1/2 the real portion of our phasor for the voltage across the 3 Henry inductor times the conjugate transpose of the current through the 3 Henry inductor. So here is my voltage phasor, and then my conjugate transpose, I just take this current, and instead of this negative 133, I'm going to have positive 133. So now when you multiply these two together, what do you see? Well, you get 6.7949. The interesting thing is these angles add up to exactly 90 degrees. And so what's happening here? If you're looking for the real portion, but look, your phase angle is now 90 degrees. What does that mean? That is all imaginary. And so there is no real portion at all right here because the cosine of 90 degrees goes to 0 and you're all in the imaginary portion. You're going to have a J times sine of 90. That's going to be J times 1 times this value here. It's all imaginary. So when you just look for the real part's 0. So the average power delivered to the 3 Henry inductor, 0 watts. Now, let's perform a similar evaluation looking at the 2 ohm resistor. So here, this is going to be a little bit trickier. Let's go back up to our schematic so we can see where to get the voltage. In this case, I'm going to treat the voltage across the inductor as one voltage, and then the 2 ohm resistor and this 1/4 farad capacitor are going to act like a voltage divider, and I can treat them like a voltage divider because now I've converted them into impedances. They have the same units, they're now in ohms. And so I'm going to take the voltage that is across the inductor and say that is divided proportionally, just like a voltage divider, across the 2 ohm resistor and the negative J 2 ohm capacitor. And so let's go back down here and let's work through that. And so if we get down to here, we can figure out that the voltage across the 2 ohm resistor is going to equal the voltage across the 3 Henry inductor times 2 ohms divided by the sum of the impedances of the 2 ohm resistor and that negative J 2 ohm capacitor. And so we can take this and just multiply by effectively 1, which is going to be the complex conjugate of the denominator divided by the complex conjugate of the denominator. The reason we want to do that is to get rid of our imaginary portion here. When you multiply this through, what do you get in the denominator? 4 plus 4, simply 8. And then over here, when you multiply this on through, you're going to get the voltage across the 3 Henry inductor times 2 plus J2, that quantity. And so if you work this on out, what you figure out is you've got this multiplied by 1/2 plus J over 2. And so here we're going to go ahead and convert this back to phasor. This is the phasor for the voltage across the 3 Henry inductor. We're going to convert 1/2 plus J over 2 into a phasor. So I get square root of 1/2 squared plus 1/2 squared, and my phasor angle is going to be the inverse tangent of 1/2 over 1/2, or just 1. And I know from a basic trigonometry class that that's 45 degrees. And then if you work out this square root, that ends up being square root of 2 divided by 2. Multiply those together. The voltage is going to be 4.5149 phasor 1.193 degrees. Now, to find that current, it's just equal to the voltage divided by the 2 ohms. And remember, that's going to be exactly in phase with the voltage. The current and the voltage are going to be exactly in phase when we're talking about a load that is just a resistor. So the phase is going to be exactly the same. We just simply divide our R value by this 2 ohm load. So we get 4.5149 divided by 2, and the phase angle 1.193. So now the average power once again is 1/2 real the voltage phasor multiplied by the conjugate transpose of the current phasor. So here's 1/2 the real. Here's my voltage phasor for the voltage across the 2 ohm resistor, and here is my conjugate transpose. Again, I just flip the sign on this angle, so I get 4.5149 divided by 2, phasor negative 1.193 degrees. When you add these, or multiply these together and add the angles together, you notice once again you get to 0 degrees. That means this is entirely real. You multiply these two together, you get 10.1922. That's all real. And so your average is just going to be 1/2 times 10.1922. So your average power delivered is 5.0961 watts. Now, moving on to our last component, the capacitor here, you can figure out that the capacitor voltage is going to equal the voltage across the 3 Henry inductor minus the voltage that's dropped across the 2 ohm resistor. Let's review why. If we go back to our schematic, which now we've gone through several pages of calculations, if you know the voltage here, and then you know the voltage that's dropped there, you can take this node voltage, which is going to be the same as the voltage across the inductor, subtract off the voltage you just calculated is dropped across that 2 ohm resistor. That's going to tell you how much voltage is dropped across the capacitor. And so we're just going to subtract those on down. We already have our node voltage there, the voltage across the inductor. We already have the voltage across the 2 ohm resistor, and so we can simply subtract those. So here's the phasor for the 3 Henry inductor voltage. Here is the phasor for the 2 ohm resistor voltage. Again, we're going to convert these back to complex pairs. We're going to end up adding the real components together, adding the imaginary components together. So I've written it this way. Here's the real component from this phasor. Here's the real component from that phasor. Add those together. Here's the imaginary components from this phasor, imaginary components from that phasor. And you add them up, you get a very small real portion here. And then you get this imaginary portion. And so you get the R value just by taking the square root of this quantity squared plus this quantity squared. You get 4.514. And then your angle, again, same thing, inverse tangent of negative 4.5139 divided by 0.094. That ends up giving you negative 88.807. Moving on down here, let's figure out the current. The current is going to equal the voltage divided by the impedance. And so here, the impedance of the capacitor is just given as negative J2 ohms. Now, let's look at that in terms of a phasor. It's negative, and it's all imaginary. And so what that means is it's going to be, if you think about the unit circle, down on the imaginary axis, there's going to be no real component to it, and it is going to have a magnitude of 2, and it's going to be all in the negative imaginary direction. And so as a phasor, that's just going to be 2 negative 90 degrees. Here is my phasor for the voltage dropped across that quarter farad capacitor. Now I just divide those on out. Here's what I get. I divide these two, I subtract those angles, I get 2.257 phasor 1.193. Now, for my final calculation, I know that the power on average that is delivered to this capacitor is 1/2 real portion of the voltage across that component times the conjugate transpose of the current. So again, I take this current, just flip the sign on the angle, multiply these on through. Hey, look here, I end up The angle, when I add these up, becomes negative 90 degrees. What does that tell you? Well, if you're looking for the real portion of that, the cosine of negative 90 degrees is in fact 0. There is no real portion there, and this again goes to 0, so the average power delivered to the capacitive load is 0 watts. And so what is the takeaway here? If you have a capacitive load, if you have an inductive load, your voltage and your current are going to be 90 degrees out of phase with one another. Whether that happens to be leading or lagging, negative 90 or positive 90, the cosine of negative 90 or the cosine of positive 90 both go to 0, meaning there's no real component to it. And what that means is ultimately your average power delivered is going to be 0 watts, because the power is going to be negative at certain portions and it's going to be positive at other portions as you're charging and discharging a capacitor, as you're inducing a current in an inductor, and then that current is flowing back on out. And so on average, capacitive and inductive loads are going to be delivered 0 watts, whereas the power is all going to be delivered, all the real power is going to be delivered to the resistors that we have in there.